Oh, thanks for the invitation and this wonderful workshop. I've learned some new interpretations of the concepts that I know. Capacity is a minimum 2 norm of an element in an orbit, and so on. I haven't updated my slides, and if you have questions about those interpretations, I think it would be better to ask Michael Walter and Keith Gard. So this is joint work with Chi Lau is in the audience, In-Tat Lee, and Akshay Ramachandran is also in the audience. So as in the title, the talk would have 3 parts. So I would first introduce what is the Paulsen problem, what is the original motivation of this problem, and then I would talk about how we solve this problem by defining a continuous version of the operator scaling algorithms, which is also known as the gradient flow. And then in the third part, we have to do a smooth analysis of the operator scaling algorithms to solve the Paulsen problem. And then I would end with some discussions and open questions. Okay, so what is the Paulsen problem? Is a problem about frames. What is a frame? A frame is a collection of vectors in d-dimensional space that span the whole space. And we said a frame has the equal norm property if all the vectors have the same length. And it has the Parsifal property if sum of the outer product is equal to the identity. Okay? So how should we understand it? We can understand an equal norm Parsifal frame as an over-complete basis when we have exactly, when n is equal to d, then it is just orthonormal basis. But we consider the range when n is much bigger than d, then it is an over-complete basis. And then we can, for example, we can still do the projection to the vectors and think of representing a message using the coefficients in the projections. And this is the interpretation that people use in designing erasure code. Even that because the basis is over-complete, even though you lost some coefficients, you can still recover what is the original message. So this is some applications in signal processing and communication theory. I've heard it is also useful in quantum information theory, although I don't know much about it, in designing measurements. So now we are interested in constructing equal norm Parsifal frames, but it seems to be a difficult object to construct. We know a few algebraic constructions, but on the other hand, we know the solution space is a non-trivial manifold, but we just know a few points in the space. We don't know lots of examples. So Paulsen were interested in constructing not only equal norm Parsifal frame, he is interested in constructing a Grassmannian frame. It's an equal norm Parsifal frame with minimal maximal inner product. He wants the vectors to be as close to 90 degrees as possible. And those are even more difficult to construct. So he was interested in the problem when we are given n and d, what would be this optimal angle that we could achieve? That the minimal, maximal inner product square. So then, on the other hand, it is easier to construct approximate solution. If we don't care about equal norm Parsifal frames exactly, it is much easier to come up with approximate solution. For example, if we generate random unit vectors, then you will satisfy the equal norm constraint, and then by matrix concentration, it will also almost satisfy the Parsifal constraint, and then they also have a somewhat large angle. And then you can start from those examples, and then you may ask, then if I found an approximate equal norm Parsifal frame with such angle, does it also exist an exact equal norm Parsifal frame with approximately that angle? So that was the question that he is interested in. And then he asked people, can we turn an approximate frame into an exact equal norm Parsifal frame by just moving the vectors slightly? didn't change the solution too much. Okay, so that was the motivation of the original problem. Is it clear? And the precise formulation is the following. So he asked, suppose we are given vectors u1 up to un in d-dimensional space. What is the best function f n d epsilon? Epsilon is a parameter which measures how much error is the input. That each ui is close to equal norm. They are approximately, the norm square is approximately d over n. And sum of their outer product is almost equal to the identity. It's between 1 minus epsilon identity and 1 plus epsilon identity in the PSD sense. And if we are given such input with n, d, and epsilon, does there exist a set of vectors in RD such that is exactly equal norm, exactly Parsifal, and we just need to move the vectors a little bit. So how do we measure the movement is sum of the ui minus vi norm square. So what is the best function f n d epsilon you can prove such that when the input is almost equal norm Parsifal, how much we need to move such that it is exactly equal norm Parsifal. Okay, yes?
Is it important that you have like rank 1 situation? Can you say instead of ui transpose will be positives in the different matrices with equal places?
Yeah, we would consider a generalization in the operator case.
Your result will work for that case as well?
Partially. One part would work, the other part we don't know yet. Oh. So there was some previous work on this problem. The first result, they make an interesting assumption. When d and n is relatively prime, then they show that the total movements that you need to do is polynomial in d, polynomial in n, and epsilon square. And their proof is based on a dynamical system which maintain the Parsifal conditions and improve on the equal norm condition. And then second result, they remove this assumption. They don't need to assume that they are relatively prime, and they prove this bound, which is polynomial in d, polynomial n in epsilon. You should think of this bound roughly as 1/7 of the first bound, which is worse, because we think of this is a small number. So their approach is based on gradient descent, which keeps the equal norm conditions and improving on the Parsifal conditions, getting closer and closer in the Parsifal conditions. And what do we know? There are also simple examples showing that the function has to be at least d times epsilon. There are examples in which you have to move at least so much. The main open question in this Paulsen problem is, can the bound fdn epsilon be actually independent of n? Independent on the number of vectors, just a function of the dimension and epsilon. Okay? So we answer this question positively. We show that it is at most d to the 7 times epsilon, and epsilon is the correct dependency on epsilon. So the proof has two parts. First, we would define a dynamical system based on operator scaling and show that this function is at most d squared times n times epsilon, which we haven't removed the dependency on n. And then in the second part, we would do a smooth analysis. We would perturb the input a little bit and show that after perturbation, it would converge much faster. And then we remove the dependency on n. Okay? So this is the first part. You have any questions so far?
Can the dependence on epsilon be epsilon to 1 even when GCD in D equals 1?
When they are relatively prime, their dependency on epsilon is better, is epsilon square.
And that's,
we couldn't explain that result using our technique. Okay, so then I would talk about the second part. I would define a dynamical system based on operator scaling and derive the bound d squared n epsilon. So how to move an approximate frame to satisfy the two conditions simultaneously? I think this is not a good question for this audience because we all know what it is. Anyway, the problem is difficult because we have to satisfy the two conditions at the same time. It is very easy to just satisfy one condition. If I want to satisfy the equal norm condition, I just rescale the vectors. And if I want to satisfy the Parsifal conditions, you can do this linear transformation to make the vectors to be identity. But of course, when you fix one condition, then the other condition may be violated, and then so on. So the hope is a natural algorithm is to alternate between these two steps and hope that it would converge to a solution which satisfies both conditions. Okay? So what was our starting point? So we observed this algorithm, and it was also mentioned in some survey of the Paulsen problem, and they showed that they didn't analyze it. And then at around the same time, we see these new results on operator scaling that they show how to analyze these alternating algorithms for operator scaling. So our first idea was, what about we analyze how much we move in the algorithms? So we start from some input, we apply these alternating algorithms and move. We want to bound the distance between the input and the output, and we bound it by the movement in the alternating scaling algorithms. Okay, so that was the first idea. But before I go into more details, let me tell you what is operator scaling. But I assume all of you know. So operator scaling is we are given a collection of matrices, k of them. Each one is n by n. And this problem, I believe, is defined by Griffiths. We want to find a left scaling matrix n by m and a right scaling matrix n by n, such that if we define Vi to be L times Ui times R, then sum of Vi transpose would be a scaled identity. Sum of Vi transpose Vi is also a scaled identity. Okay, for some constant C. And then we set an operator such a Vi satisfying both conditions, they are doubly balanced.
You assume that L and R are invertible, or you don't want to assume this? Otherwise, there is no group.
Do I need to assume L and
L and R,
they are invertible? Yeah.
that's the assumption.
Oh.
No, it's not assumption.
Yeah, we would find. Oh.
That's the problem.
We want to find L and R, and then L and R will be invertible. So I also want to mention some applications of operator scaling, but I also think most of you know. But anyway, so the simplest case of operator scaling is matrix scaling, which already has. Operator scaling looks like a very simple problem, but it has surprisingly many applications. So matrix scaling is a simple case, and it already has applications in solving linear equations, bipartite matching problem, approximating the permanent. Frame scaling is the case that we are interested in. We are given vectors, and we want to scale such that sum of the outer product is identity and they have equal norm. So this is considered by Foster, and he proved that under some conditions that a frame can always be scaled to an equal norm Parsifal frame, and he used it to prove psi rank lower bound of the Harder-Mount matrix. And then there's also some applications in machine learning, and our problem is a case of frames scaling.
So the definition of frame implies general position?
No.
But he needs general position.
Yeah, but in bulk you don't need general position, and also in bulk completely you don't need general position.
Right.
Also, is the right
Yeah. It's only a sufficient condition. And then there's also a common generalization of matrix scaling and frame scaling, which I call PSD scaling. It's not the right name. And is used in approximating the mixed discriminant. And then operator scaling, now we know it has some very nice applications in computing the non-commutative rank, computing the Braskamp-Leib constant, and then very recently used in this orbit intersection problem that we have all seen in this workshop. I just want to mention that in this orbit intersection problem, they have actually used our result in the operator Paulsen problem, that our generalization, although it was not mentioned in the talk. So what is the alternating algorithm for operator scaling is also very natural. We have two constraints to satisfy. If we just want to satisfy sum of UI transpose is equal to identity, we can apply this left transformation. To satisfy sum of UI transpose UI is equal to identity, we can apply this right transformation. And then we just repeat these two steps and hope that it would converge. Okay? So this is the alternating algorithms. So now I want to show you that the frame question that we have can easily be formulated as a special case. We are given vectors UI in RD. For each vector, we would construct a matrix UI, big UI, which is D by N. We just put our vector into the ith column, and all the other columns are 0. Okay? For each vector, we construct a matrix with only one column being our input, all the other columns being 0. And then the conditions in the operator scaling case, sum of UI transpose is equal to the identity, is just the Parsifal condition. Just sum of the outer product is equal to the identity. And then the condition that sum of UI transpose UI is equal to the identity, sum of UI transpose UI, if you write it down, it would just be a diagonal matrix where each diagonal entry is the norm square of a vector. So if we require it to be equal to identity, then we are just saying each vector should have equal norm. So the alternating algorithm that I described about frame is a special case of the alternating algorithm for operator scaling. So for this part of the talk, we focus on this more general setting, and we define a generalization of the Paulsen problem in this operator setting. Okay? So let me define this generalization. It's very similar. Now we are given an operator U1, UK, each is an M by N matrix. Sum of UI transpose is close to identity. So this epsilon is how close it is to identity. Sum of UI transpose UI is also close to the corresponding scale identity. And then we want to find V1 up to Vk such that the two conditions are exactly satisfied. And we want to bound how much we need to move. So instead of using the two norms for vectors, we just use the Frobenius norm for matrix. So we just think of a matrix as a vector. And then we want to bound what is the best function that we can prove if we are given such input, how much movement that we need to make in terms of M and N, K and epsilon. And we will show that in this part, that it is at most M squared times N times epsilon. That would imply in the frame setting, it is at most D squared times N times epsilon. Okay? So this is the setting that we would focus on in this part of the talk. The operator case.
So you don't already change the notation, the number of vectors was N and now it's the number of vectors K. What you eliminate is the dependent in the number of operators.
Right.
It's just that
Yeah.
N became K here.
In the frame setting, K is equal to N. M is equal to D, N is equal to N. Okay, so now going back to our first idea that when we want to analyze the total movement of the alternating algorithm, that is discrete version, there are some issues that we don't know how to avoid. So there are examples which do not converge. It may not have a scaling. When you apply this scaling algorithm, if I start from the three vectors on the left-hand side, I do a scaling. In one step, I would get this to satisfy the Parsifal constraint. And then when I scale it back to satisfy the equal-norm constraint, I get back the original input. It doesn't converge. It would run into infinite loop. And even if we assume that the input is in some general position such that it is always scalable, this issue would not go away. Instead, we would have, you can imagine if we just change the input a little bit, then maybe it would converge, but the path that we are going to take would zigzag a lot. And then if we want to bound the distance between the input and the output by the path, then that would be a very bad bound. And in fact, we do the calculations and we do not get anything better than the trivial bound. So this approach directly doesn't work. Okay, and so our idea is to define a continuous version and hopefully to avoid this zigzag problem that we want to do the two steps simultaneously, not alternating, and we just want to move very continuously infinitesimal steps instead of making a full step. So let me tell you what is our dynamical system, and I would explain to you why it is a continuous version of operator scaling. So the definition is this, that the change of the UI, I would need to define what is S, is Si minus M of the sum of the outer product times UI plus UI times. The right scaling matrix is Si minus N times the sum of Uj transpose Uj. And what is S? S is we define as the size of the operator, which is just sum of the Frobenius norm of the matrix. Okay? So this is the definition. We would move our operator using this formula. So at every time, the change of UI is defined by this equation. Okay? So it may not look like the operator scaling algorithm at first glance. So let me explain how we come up with this dynamical system. So in the discrete case, if we just look at one step, we are doing this transformation. UI goes to sum of Uj transpose to minus 1/2 times UI. So in the continuous case, we just move very little. So we would just, instead of 1/2, we have dt. And then we want to write it. And then what we do is we scale this matrix by a factor of m over s, such that it is close to the identity. It is approximately equal to identity. And then we just apply Taylor expansion and to get this. So that would correspond to the first term. Second term also comes up the same way, and then we just add the two steps together and define our dynamical system. Okay. So this is how we come up with it, and now we know from this workshop that it is just doing gradient flow. I would explain about that connection later, but we didn't know that when we work on this problem. Okay, so any questions?
Is there maybe, I know the right-hand side can be interpreted as a gradient of a function somehow, or not? Usually if you have a dynamical system.
The whole thing can be understood as the gradient of something that I haven't.
Tell us what is the something?
That I haven't shown you yet. It would be the.
I mean, we want to move in some manifold, so there's these two conditions. preserved, and then by construction will stay in the manifold. I
Oh.
guess. I mean, the sum of the UJ's transpose K should be identity for the other way around also.
Oh.
No, only the limit will be identical.
Really?
When you start, it is not like that. It's just close to like that. When you start, it's just close.
Right. Correct. We want to go then.
Yeah.
So then it will be a deviation of this, the function then. So,
What is your question?
okay.
Oh.
I'm just trying to figure out what is the function.
Oh, okay. I would tell you.
But inner nodes were
Whatever
all capacity.
whatever capacity means.
Yeah, all nodes were anyway. It's
So by the way, actually it's a cubic system, right? So potentially can explode in a finite time interval. So you need some kind of Lyapunov which tells that it's not doesn't explode.
Oh, it won't. Yeah, I would explain.
Ah, okay.
Oh. So now the idea is the same. We want to bound the distance of the input to the output by the path length. But instead of using the discrete system, we use the path of the continuous system. And hopefully it won't zigzag. And then we can get a good estimate of the distance. So the distance that we want to bound is the output. Output is UI infinity when the dynamical system goes to time infinity minus the input. And then you can rewrite it as the integral of the change of the UI. So it is just by definition. And to bound it, we would use triangle inequality to bound this. So from 0 to infinity, this is the local movement. We call it the local movement. At each time, how much you change the matrices and the 2-norm square of that. Okay, so to bound the final distance, we use triangle inequality to upper bound it by the path length. So you should think of this right-hand side is the blue path length, the left-hand side is the red line. Okay. Okay, so now an important quantity in our analysis is this progress measure. Instead of using the error measure that Paulsen defined using epsilon, we are going to use this error measure, how close we are to doubly stochastic. And this is the error measure defined by Griffiths when he studied operator scaling, is the Frobenius norm of that two matrices. I can give you some intuition why it is easier to use delta instead of epsilon in the Paulsen problem. So in the Paulsen problem, we are given input, and we said is between 1 minus epsilon and 1 plus epsilon identity. So if we look at the eigenvalues of the matrix, we are just saying that the eigenvalue should be between 1 plus epsilon and 1 minus epsilon. So it is an L infinity norm bound on the eigenvalues. So that is the input of the Paulsen problem. But if we look at the delta is the Frobenius norm, is just a 2-norm square of the eigenvalues. So it is easier to work with 2-norm. So this is one reason that delta would be a better parameter to measure the progress. Infinity norm is difficult to argue that it is decreasing all the time and so on. So that is one reason. And then delta also has a few nice properties. So the first property is true by any distance measure. It is equal to 0 if and only if the operator is doubly balanced. It is equal to 0 if the two matrices are 0, which means that the UI is already doubly balanced. It will satisfy the two conditions exactly. Okay? So, and you can show, it is not difficult to show, delta is at most m squared times epsilon squared by this L2 L infinity relations. So we would focus on proving that in the later of this part of the talk, we would forget about epsilon. We would just try to focus on proving the total movement would be m times n times square root delta. So delta is the correct error measure to analyze the progress of these algorithms. And then once we get this bound, then we put the relation between delta and epsilon, we would get m squared n times epsilon. So we will focus on proving mn times square root delta. So why it is the correct measure, there is now also a good explanation for that. The dynamical system that we define, although we didn't know it, is actually moving in the direction that minimizes delta. Is equivalent to the gradient flow. You come up with this error measure, and then you move in the direction that minimizes delta. So this is a good quantity to keep track of the progress. Okay, so now we will start to analyze the convergence of these continuous operator scaling algorithms. We found some nice identities to analyze it. So one is when we compute the derivative of the size, we show that ds is equal to minus delta, the change of the size. So in particular, the input would keep shrinking, decreasing in size. Delta is a non-negative quantity, so ds is always a negative number, so the size of our input would keep shrinking. And the second identity is change of the delta. Delta is the quantity that we care about. We want to drive delta to 0. Change of delta has a very nice form. It's exactly equal to minus of this term, where this term is the local movement. So if we move more, then delta would decrease more. So whenever we move, we decrease the delta. So now with this gradient flow interpretation, actually this formula has a nice explanation. You just write d delta dt as du over dt times d delta over du and du dt. And then by the definition of gradient flow, you would get this. But at that time, we didn't have this interpretation, and we were actually a bit lucky to find this formula by lots of trial and error. So now with these two lemmas, I would first show you that the dynamical system would always converge, unlike the discrete case. That by lemma 1, the size is always decreasing. And then by lemma 2, there is exactly the second derivative is positive, so it is convex. And then when we look at time infinity, by lemma 1, delta would be equal to minus of the change of s. But because of lemma 1 and lemma 2, the change of s at time infinity must be 0. There's a limit. And so at time infinity, we would get an output that delta is equal to 0. So our operator would be doubly balanced in the end. So you may wonder what happened to those inputs that are not scalable. For those inputs that is not scalable, it would actually converge to 0. It is closely related to what you guys have talked about. The minimum norm becomes 0. It is in the null cone. And okay. So we can analyze U infinity. We know that U infinity is a doubly balanced operator. Okay, and now the lemma 2 is also very useful in analyzing, in bounding the distance. Remember, we want to bound the distance, and then we use triangle inequality and use the path length to bound the distance. And that term is the local movement. And then by lemma 2, the local movement is exactly equal to this. So the total distance that we need to travel is related to delta. Is related to how delta would change over time. So it's a nice connection between the distance and delta. Okay. So now we want to bound the right-hand side. How quickly delta would change to 0. If delta would change to 0 quickly, then this term would be small. If delta decrease slowly, this term would be big. So I just, from this slide, I square both sides. Instead of distance, I use the square distance, and then that would be the square of the right-hand side. Now I want to bound this term, integral of square root of the change of delta. In order to bound this, from time 0 to time infinity, our idea is just to bound, we define this term called half time. Half time is the first time t, because delta is decreasing, we just want to bound this integral from time 0 to time t such that delta is decreased by a factor of 2. If we can do that, then we can bound it by a geometric sum arguments that it would be at most a constant factor times that. So we are going to bound that. And then to bound this term, the right-hand side, we simply apply Cauchy-Schwarz inequality, and then we get this. So the first term is just t, the second term is at most delta 0. So in order to, so what we have reduced so far is in order to bound the total distance that we have moved, we just need to bound what is the time, what is the first time delta becomes delta over 2 in our continuous algorithm. Okay, so it just remains to bound the half time. And in order to bound the half time, we have to use the capacity defined by Griffiths, which is a potential function to analyze operator scaling. So the exact form may be a little different from Griffiths' papers because we have to do some normalizations such that it is consistent with our size, so that they have the same scaling factor and so on. But you don't need to look at the exact definition. We just use a few properties of the capacity function. So in our dynamical system, in the discrete case, the capacity is always increasing. But in our continuous case, we can prove that the capacity is unchanged over time. It is the invariant in our algorithms. I'll just give a quick explanation why this is true. We know how capacity changes when we scale by left and right matrix. We have an exact formula for that. And I just want to show you that in our system, the determinant of the left and the right matrix would be 1, and then capacity would be unchanged. Why is that? Because in our system, the left matrix and the right matrix, they are defined such that they have trace 0. So if they have trace 0, intuitively, what it means suppose we have these differential equations and pretend every matrix is just a scalar, then we would solve x is equal to exponential of L times.
So, excuse me, you're talking now about general case or your original, when those UIs?
Now I'm talking about the operator case.
No, those, the operator, it responds to those rank 1, or you talking about general case now?
General.
So, but even in general case, so you probably, I'm just curious, so I think here you can keep the x as a diagonal matrix for this specific operator which we use.
Can we assume x to be?
Because the operator here is you take x, you take diagonal of x multiplied by those matrices and you add. This is the things which we do.
But in general, the infimum of capacity will not be.
No. In his original formulation, by frames.
Oh, in the frame case, we can assume x to be diagonal.
Oh, this is exactly. Yes. Okay, this is what I mean.
In the rank 1 case, you can assume that.
No, not necessarily. It is his general case. It's always around
about your answer to his question. This is a completely general operator scaling. The UIs are arbitrary.
Yeah. But what he said is correct. In the frame case that the original Paulsen problem that X can be assumed to be diagonal, it is actually what we use in the second part as well. So if the trace of a matrix is equal to 0, then the determinant of this matrix is equal to 1. So that when we do the scaling, capacity doesn't change. So that's the rough idea. Capacity doesn't change in our system. And then the final ingredient of the first part is this capacity upper bound and capacity lower bound. The capacity is always upper bound by the size, is always lower bound by the size minus mn times square root delta. This proof is very similar to the proof in the GGOW paper. We need to change the proof a little bit because it's in the continuous case, we don't have one condition satisfied, and we also work on the normalization and get this bound. But proof ideas are very similar. And one...
This is just arithmetic mean, geometric mean inequality. No, basically, or not?
No, reduce to the matrix case, and then in the matrix case, we move this matching. And one particular implication is when t is infinity, S infinity is equal to cap infinity, because when t is infinity, delta infinity is 0. So we have equality, and then capacity is unchanged. So the size that it would converge to, in the end, is the capacity of the original input. So we would come back to this lower bound. We won't redo the proof, but would come back to this lower bound later in.
I have a question. So this result which you mentioned, you generalized. So roughly it says like this, that for some polynomial, the determinant of that if you know that gradient is small, then you close to the experiment. Okay? This is essentially this is the essence.
Yeah. That's what Michael Water told me.
Okay, so
2 days ago.
okay, good. So you see, makes sense what I'm saying.
So
The one, so
S is the current 2 norm. Capacity is the optimal 2 norm, and delta is related to something in
so essentially
the gradient.
Is that because again, small gradient implies that you close. So I'm just curious, can you use this also self-concordance results to close this property? Because it's, but anyways.
So now we just need to, now with these 2 lemmas about capacity, we can bound the half time. Okay, what is the time, what is the first time delta would becomes delta over 2. So by lemma 3 plus lemma 4, we know that the size of time t, big T, is at least the capacity of big T by the upper bound. Capacity unchanged, capacity T is equal to capacity 0, by the capacity lower bound is at least size 0 minus mn square root delta. What does it mean? It means that the size of the operator would decrease by at most mn times square root delta. This is the total decrease of the size by the 2 results of the capacity. It bounds how much the operator would decrease in size. So it gives an upper bound on how much the operator would shrink. But on the other hand, by the definition of the half time, and lemma 1 said if delta is big, the size would decrease fast. So if the half time happens very late, we have decreased the size a lot. So the size would decrease by at least, in all of this time, the decrease of the size would be at least delta over 2. So this is a lower bound on the size we would decrease. And then you just combine the upper bound and the lower bound. It says you cannot decrease for too long. So delta have to be at least at most delta over 2 after so much time of the dynamical system. And then that would imply total movement is t times delta, which is mn square root delta. And we are done for the first part. So let me summarize. Again, we want to bound the distance by the path length. It's a simple idea. This is the square distance. We want to bound it by the path length. This is the path length. And then by the lemma, the local movement has this very nice form, square root of the change of the delta. And then in order to bound this term, instead from time to 0 to infinity, we bound it from 0 to t, define the half time, and then use geometric sum, use Cauchy's force to get t times delta. We need to bound the half time t. In order to bound the half time t, we used the capacity defined by Griffiths and the two lemmas and also lemma 1 to show that t is at most mn over square root delta. And then finally, from delta, we just use the relation between 2 norm and infinity norm, and then we get this bound for the general operator Paulsen case. Okay? So this is the second part.
But it applies to general operator, so this is not Paulsen problem.
Right. Yeah.
General computer process.
Yeah. Okay, any questions? So now I want to talk about the smooth analysis. So the second part has a pretty clean proof that I could present into some details. The third part is a little messy, so I'm just going to give you the proof outline, what is the main ideas to remove the dependency on n. Okay, and this is an important remark that the third part, the smooth analysis, only works in the original Paulsen setting. It doesn't work, not yet, we don't know, in the general operator setting. So what we have done in part 2, we can understand it as a reduction of the total movements to capacity lower bound. So as long as we have a capacity lower bound, cap is at least the size minus some function of dn delta, then we can prove that the total movements that we need to make in the dynamical system is this function, f dn delta. And in fact, I think maybe this reduction is also useful in more general setting, like in the tensor case, we haven't considered, but we believe maybe similar conditions would be true as long as you have a capacity lower bound in the tensor setting, you can also upper bound the total movement you need to make in the continuous algorithms. So in the second part, we prove that for any input, this fdn delta, I missed a delta here, is at most dn square root delta. And then in this part, I want to show you that if we have some perturbed input, some random input, then we can prove a much better capacity lower bound. There would be independence of n, and that's where we get the distance is also independence of n. Okay? So what is our idea? We actually don't have a very clear idea, but we just have the intuition that operator with small capacity, they are very rare. It's very difficult to construct such operator. So then we just want to randomly perturb the input and then say that if we perturb the input, then they would not be those worst case, and then we can just apply the dynamical system. So the plan is the following. We have our original input, we perturb the input, and then there would be some movement in this step. And then after perturbing the input, we want to just apply our dynamical system and show that it would converge much faster and get a doubly balanced output. And then we measure the distance of the input and the output by the sum of the two steps. And maybe one intuition why perturbation would work. Our intuition mostly comes from the matrix setting. So in the matrix setting, we know capacity is implicit in James' talk. Capacity is equal to the KL divergence of our input to the space of doubly stochastic matrix. And KL divergence is large because we have restricted the support. But by our perturbation, if we perturb, then the support size would be very large. And then intuitively, the KL divergence to the space would be much smaller. So that is one intuition that we have, but although we don't use it in the proof. So now here's the plan. Remember, the movement in the dynamical system would be a function of d and n and the delta of the perturbed input. So now we want to achieve three things in order to bound the sum of the two distances. First, we want to upper bound the perturbation movement. So that would be very easy if we do some standard perturbation. We know exactly how much we moved. And then second point is more difficult. We need to show that the error won't increase too much, that the delta of the perturbed input is approximately the delta of the original input, because if we perturb and then we increase the error a lot, it's not worth it, and then we have to move a lot.
Chief, for your intuition about the support to be able to hold the perturbation has to be really big in every coordinate, right? I mean,
Oh, we just need to add a small, from 0 to a small epsilon, and then the support size would be large. So we just need to move a little bit.
but it's epsilon in every, everywhere, not just.
Right, yeah.
I mean, in particular, you're really dimension independent. So if you move epsilon in any coordinates.
It doesn't care about the dimension, it just cares about the number. It wants to remove the dependence on the number.
No, but if you mess up the error points in the bound, if you change epsilon to a function of n, then you lost the game.
Yeah. And then we want to show that after the perturbation, then the new instance, the capacity bound would be much better. Would have no dependency on n. So that would be the main ideas of the proof. So what is the perturbation process? Let me just describe. Basically, you can just think of adding random Gaussian noise. We first generate a vector in RD. Each entry is just IRD Gaussian with variance sigma square. And the only technical condition that we impose is the Gaussian should satisfy the two linear equations. One is the inner product of GI and the ith vector is 0, and then sum of the outer product is equal to 0. This is, I would explain very soon why we need these two conditions. And then we just set the vector to be UI plus the noise project into the space that satisfy the two conditions.
So the noise is just the independence Gaussian. So
The
very correlated noise is the same noise applied to all of the vectors.
No, each vector would have independent noise. So
You have n vectors.
we have n vectors, d coordinate for each. So we would have d times n.
Or d times n, so it's independent.
What is the reason that we do the projection? The reason we do the projection is to ensure that the delta won't increase too much. Because when we add the noise and we compute the new delta, those two terms are exactly the cross term, the first order term of the error. So we just want to set the first order term to be 0, and then the second order term would be small. So this is it is a little messy, but the intuition is we have dn random variables, we have d vectors and n vectors and d coordinates, but the subspace that we are restricting to is just of the dimension n plus d square. So the second constraint is a d by d matrix, is d square linear equations. The first constraint is n equations. So n plus d square dimension, we have so much freedom. Intuitively, they're enough, and then we just didn't change the analysis too much. So this is one technical step to prove that delta doesn't increase too much. And the main work, the most important part is proving the improved capacity lower bound. So how do we do that? We look at the proof of the capacity lower bound. There was a reduction from operator capacity to matrix capacity. So this is the operator capacity, and we restrict to the frame case such that x is diagonal. This is used in our analysis. And then there's a reduction to matrix capacity basically by eigenvalue decomposition.
On the previous slide, I guess I missed why. Can you go back one?
Sure.
Okay, so you said delta U2 is about the same as delta U.
If we add random noise.
Yeah, do you have what is the heuristic to see that this is true?
These two terms would be the first order terms, and then we need to analyze the second order term. Yeah, I don't have very simple explanations of that. So there is a reduction from operator capacity to matrix capacity, and then we can just analyze the matrix case. So the new ideas that we have is we can actually use our dynamical system to give good lower bound for matrix capacity. So remember in part 2, we use capacity lower bound to bound this half time. So we use capacity lower bounds to say indirectly that delta would eventually decrease to delta over 2 not too long after. Indirectly argue about the convergence of delta. So in this part, we would do the other direction. We show that under certain conditions, we can directly argue the convergence of delta. And then that would imply capacity lower bound for the matrix case. And then,
They were standard Gaussians that you used for?
yes, standard Gaussian, but subjected to 2 constraints.
Okay, so variance one,
Variance sigma square,
which sigma is?
the parameter that we would choose.
I believe the sigma equals 0, then the error is causing a problem.
I will show you the choice of sigma square soon. Well, not soon, but in the end. Okay, so this is the idea. We use our dynamical system. Let's say, suppose we can directly argue about under certain conditions that the decrease of delta is at least mu of delta for some mu, which would imply that delta is decreasing exponentially. Suppose we can directly argue that. Then we can use it to give improved capacity lower bound, because what we want to bound, we want to upper bound the size minus the capacity. We know that capacity unchanged, so cap 0 is equal to cap infinity. And we also know that cap infinity is equal to S infinity. We explained before, it follows from lemma 4. And so we just need to bound the size of the input to the output, but this is governed by the delta change, as I can, so we rewrite it, it's just the integral of the change of S. And by lemma 1, the change of S is equal to the change of, is equal to the delta. And we know delta is exponentially decreasing. So we have this, and then that integral is just exactly equal to 1 over delta, 1 over mu. So if we can directly argue about that delta is exponentially decreasing, we can use it to give a better capacity lower bound. So in the previous part, we use it in the other way. But in this part, if we can directly argue about delta, so there's a close relation between capacity and delta in the proof. Okay, so now to summarize, if we can directly argue about this, then we can show that the capacity would be at least S minus delta over mu. We have to show you what is mu. I'm going to tell you soon. So now we need to show the fast convergence of delta in perturbed instance. I want to show that in a perturbed instance, there would be some nice property. With this nice property, I can directly show the left-hand side, which would imply the right-hand side. So what is the pseudo-random property? I won't define precisely, but intuitively, roughly speaking, in the matrix case, most entries of the matrix is at least sigma square. We add noise, sigma square is our noise. Suppose we have this matrix, and then each entry we add noise. And most entry of this matrix is at least sigma square, then we can directly show that the convergence of delta is fast. So in fact, we would have the change of delta is at least sigma square times n times delta, which would imply the capacity lower bound is this. And then roughly speaking, this factor of n is how we remove the dependency on n on the distance bound, because we have an n in the denominator. So the factor of n gained here is the reason that we can remove the dependency of n in the total movement. So this is the second ingredient of the proof. This proof is also a little messy. It's based on some combinatorial arguments. We have a formula for the change of delta, and then we do some case analysis, some combinatorial argument and lower bound that term. I don't have very good explanation for this part as well. Okay, so now I try to combine what we have done so far and the third ingredient as well. What we want to show is if we have capacity lower bound in the frame case, we can bound the total movement. That's what we have done in the second part. And in order to bound the capacity, we follow the reduction that was done before to reduce to the matrix case. And then what we do in our smooth analysis is we add noise in the frame. And then we need to show that if we add noise in the frame, if we follow the reduction in previous work, then the matrix would have pseudo-random property, the property that I described. Most entries would have noise, would have a value at least sigma square. So this is the third technical ingredient of the proof, which is also a bit messy. But once we have this, after we add noise in the frame, we follow the reduction, the matrix would have the pseudo-random property. And then once we have the pseudo property, we can directly argue about the convergence of delta in that matrix. And then that would imply the matrix would have good capacity lower bound, which is equal to the capacity lower bound for the frame. And then we get our result. So if I want to be more concrete, we add noise, we would have the pseudo-random property for sigma square, and then we can directly prove that in such matrix, this is satisfied. The delta would decrease quick enough. That would imply capacity lower bound by the argument that I just showed you. And then by the reduction we follow, we have the same capacity lower bound for the frame case. And then for the frame case, we have, by the second part, we would have the total movement bound. So it is a little indirect. If we can directly argue about the convergence of delta in the frame case, then we don't have to go through all these steps, but we don't know how to do that yet.
You called it a pseudo-random property, which is good. It seems like it's a property, you didn't maybe formally define it, but you said all the entries are, or most entries are at least sigma squared. Is this enough? Or does it need to have randomness? Because maybe there's a deterministic...
No, it's a deterministic condition.
It's a deterministic, so
Mo-
maybe there's a deterministic perturbation that already does the job. Maybe you don't need to randomize.
Right. We don't know how to do that. Yeah. So we know the conditions. So in principle, we should be able to find a deterministic way to move in that direction, and then we don't need to add randomness. But the way to satisfy the conditions for us, we just randomly perturb.
So there is an analogous problem that arises if you want to give a strongly polynomial algorithm to matrix scaling, which we do in this paper with linear and some odd-nixty. And then we have a deterministic perturbation, and it's sort of
I see.
it's a sort of pre-processing step, which you scale once. The matrix it has the same problem. It's very far from.
And you didn't change the support in the deterministic.
No, it's a scaling.
I see. Nice.
It's based on some optimization problem, the assignment problem. Anyway, it's a deterministic step after which
It converges faster.
you somehow can assume it's more or less like you are in the situation that you are forced.
Yeah, we don't believe it is necessary. For example, in particular, we don't know whether there exists a scaling solution that would solve the Paulsen problem. We don't need to do perturbation at all, maybe, but we don't know the answer. So now, James, we set sigma squared to be this, and then we can plug into the bound, and then this is the total distance moved, and then this is the movement in the noise adding step. So you may wonder why I didn't balance these two terms. There's also some hidden technical condition that we have to set the noise to be so much such that the pseudo-random property is preserved throughout the dynamical system, that the delta decrease. This inequality is true for all time. It is true in the beginning after we add noise, but we need to preserve this property, and then there's some technical condition. We need to set the noise to be so large. And there are also some technical conditions that we need to assume n is large enough, delta is small enough, and then combining all of these, we get the d to 6.5 epsilon bound. But most of the main ideas are discussed. So that's the end of the third part. I just want to end this talk by some discussions. We studied this Paulsen problem using tools from operator scaling, but we end up developing some new techniques in analyzing operator scaling as well. Our techniques can be used to bound some mathematical quantities in scaling problems. For example, under some situations, under the conditions, the pseudo-random conditions, we can show better condition numbers of the scaling solutions. For example, matrix scaling, the largest entry divided by the smallest entry, and then they are used in fast algorithms for scaling problems. And also under the same pseudo-random conditions, we can also show that the Bascom-Lieb constant is small by directly bounding it. So one question that we are working on is to come up with better conditions instead of that conditions, most entries is at least sigma square. We hope to find better pseudo-random conditions, deterministic conditions that would show fast convergence of the operator scaling algorithms. And then we believe that would imply better average case analysis and also worst case analysis. One particular question that we are interested in is, in the Paulsen problem, it makes sense to have random input and scale. We want to show that if we are given random input, the convergence is faster. It's actually better than d epsilon. We hope to show maybe we can even get d epsilon square if we are given random input. So this is one direction that we are thinking about. And there are some concrete open questions. The worst case bound, we believe d epsilon is the tight bound, but we need to simplify our proof in order to achieve that. And then efficient algorithms to solve the Paulsen problem with dependency log 1 over epsilons after this operator scaling algorithm, I think should be doable. And also, in the third part, we can only do the smooth analysis in the frame case. We cannot do it in the operator scaling case. And we also think that should be possible, but it would just be more complicated. So we also want to do a smooth analysis of operator scaling. Given random operator, we show maybe fast convergence of the alternating algorithms. So that's the end of my talk.